brilliant sun-powered machine that literally dictates everything about our daily lives. I'm talking about the Earth's atmosphere. Have you ever wondered how a beautiful sunny day in one part of the world is directly connected to a massive thunderstorm somewhere else? Well, it's not magic, it's just pure mechanics. We're going to look at the Earth like it's a giant, perfectly interconnected engine, and we're going to map out exactly how the whole thing operates. To understand how this global engine actually works, here is our roadmap. First, weather versus climate. Second, Earth's heat zones. 3, atmospheric pressure belts. 4, the world of winds. 5, humidity and cloud formation. And finally, number 6, forms of precipitation. Let's get right into it. Section 1, weather versus climate, the timeline. Okay, let's dive into our first piece of the puzzle. Before we actually get into the gears of the machine, we really need to clear up a super common misconception about the timeline of our atmosphere. People use the words weather and climate interchangeably all the time, right? But they actually represent totally different scales. Weather is just what you experience when you step outside your front door right now. It's the state of the atmosphere at a given place and time, and it's constantly changing. Sunny one minute, pouring rain the next. Climate, on the other hand, is the grand average. It's the overall condition of those weather elements mapped out over a massive 35 to 40-year time frame. So basically, climate is the long-term personality of a region, whereas weather, that's just its current mood. Section 2, Earth's heat zones, fueling the machine. Now that we know our time frame, we really need to look at what actually fuels this planetary machine. Because every engine needs a power source, right? And ours is sitting 93 million miles away. The sun is constantly radiating heat and light energy. But what actually matters for our weather is a concept called insolation. Insolation is simply the incoming solar radiation that actually reaches and gets absorbed by the Earth's surface. Now, here's what's absolutely crucial to understand. The sun doesn't heat the atmosphere directly. It heats the ground first. Then, the Earth acts kind of like a giant radiator, warming the air resting right above it. But because the Earth is a sphere, this fuel is distributed really unevenly. And here is the result of that uneven heating. The Earth is basically divided into 3 major heat zones based on the angle of the sun's rays. Right in the middle, between the tropics, we have the torrid zone. Because the sun's rays hit here almost directly straight down, it receives maximum insolation. It's the absolute hottest part of the Earth, which is exactly why your tropical vacations are so warm. Moving further out, the temperate zones receive slanting rays, giving them much more moderate temperatures. And finally, you've got the frigid zones near the poles. These get the absolute minimum insolation and remain freezing cold. This fundamental temperature imbalance right here is what sets our entire weather engine into motion. Section 3, atmospheric pressure belts, weight of the air. So this uneven heating leads directly to our next domino in the chain, and that's atmospheric pressure. Basically, heat dictates pressure, and pressure dictates movement. We almost never think about it, but air actually has physical mass. It's got physical weight pressing down on your shoulders right at this very moment. At normal sea level, that weight exerts a pressure of exactly 1013 millibars. But here's the real key to the whole system. That pressure changes based on temperature. When air gets heated by that hot torrid zone we just talked about, it expands, gets lighter, and rises. That creates an area of low pressure. But when air is cold, like up in the frigid zones, it compresses, gets heavy, and sinks down, creating high pressure. Now, think about how these forces wrap around the entire globe. Because of that unequal heating we just went over, combined with the rotation of the Earth itself, the atmosphere naturally settles into distinct belts. We've got the equatorial low-pressure belt running right around the middle, and that's flanked by subtropical high-pressure belts, and eventually the polar high-pressure belts at the very top and bottom. So the Earth is essentially wearing these invisible horizontal bands of varying air weights. Section 4, the world of winds, seeking balance. Well, nature absolutely hates an imbalance. You can't just have heavy air piled up right next to empty spaces of light air without the atmosphere trying to fix it, right? And that brings us to the great equalizer of our engine. To equalize the immense weight differences between all those belts, air simply has to flow from areas of high pressure over to areas of low pressure. And that simple horizontal rush of air desperately seeking balance, that is exactly what we call wind. It's literally just the atmosphere's way of trying to perfectly redistribute all the heat and weight across the globe. Let's zoom in a bit and see how this builds into periodic winds, which actually reverse direction predictably. Take a look at sea and land breezes. During the day, the land heats up way faster than the ocean. That hot land warms the air right above it, making it rise and creating low pressure. Then the cooler, heavier, high-pressure air sitting over the ocean just rushes in to fill that gap. Boo, that's a sea breeze. But at night, the whole system completely reverses itself. The land cools down faster than the sea, shifting the high pressure onto the land, which then pushes a land breeze out over the water. It's like this daily rhythmic breathing of the coastline. And on an even smaller scale, unique local geography generates winds with highly specific characteristics and honestly, some pretty fascinating names. Just look at these examples. In northern India, you've got the Lu, a hot, dusty wind sweeping through in May and June. In North America, the Chinook blows down the Rockies. It's so warm and dry, it's literally nicknamed the Snow Eater because of how incredibly fast it melts away the winter snowpack. Over in Europe, the Föhn blows across the Alps, and its warmth actually helps ripen grapes in the dead of winter. And down in Northwest Africa, the Harmattan brings cool, dry relief from sticky, damp heat. Every single local wind is just a micro-reaction to temperature and pressure. Section 5. Humidity and cloud formation. Invisible moisture. As all these planetary and local winds travel across the globe, sweeping over oceans and lakes, they pick up the next vital ingredient in our causal chain: water vapor. We measure this moisture as humidity, but there is a super important distinction to make here. Absolute humidity is just the raw data, like the actual physical amount of water vapor floating around in a cubic meter of air. But relative humidity? That's the crucial metric for our weather engine. It's a ratio, given as a percentage, of how much water the air is currently holding compared to the absolute maximum it could hold at that specific temperature. You see, warm air can hold a lot of water, but when that moist air cools down, its capacity shrinks. When relative humidity hits 100%, the air simply cannot hold another drop, and that invisible vapor is forced to become visible. So when that moist air rises and cools past its capacity, condensation takes place. The water vapor gathers around microscopic bits of dust and smoke to form clouds. And depending on exactly how and where this happens, we get totally different formations. High up in the freezing atmosphere, you get cirrus clouds, these wispy hair-like structures made entirely of tiny ice crystals. A bit lower down, you might see uniform gray layers called stratus clouds, which are the ones that usually bring us a steady drizzle. And then, of course, we have the cumulus clouds. These are dense, widespread, with flat bases, your classic fluffy clouds that can sometimes tower all the way up into fierce thunderclouds. Section 6. Forms of precipitation. What goes up? This beautiful process of condensation brings us right to the final result of our atmospheric engine. The wind has moved the moisture, the cooling has condensed it, and now gravity takes over. The really crucial point here is how this air gets forced upward to cool in the first place. Let's look at one mechanism step by step: orographic or relief rainfall. Imagine wind pushing a massive block of moist air across the land until it slams into a mountain range. The air literally has nowhere to go but up. As it's forced up the mountain slope, it rapidly expands and cools. The relative humidity maxes out, heavy clouds form, and it dumps massive amounts of rain right on that windward side of the mountain. By the time the air crests the peak and comes down the other side, it's completely dry, creating what we call a rain shadow. Now, while orographic rainfall uses mountains as a literal ramp, the exact same physical rules of rising and cooling apply to other types of rainfall too. For instance, convectional rainfall. This happens a lot near the hot equator. The scorching earth heats the air right above it, causing it to rise rapidly in these strong vertical currents, which leads to super heavy, localized afternoon thunderstorms. Then you've got cyclonic or frontal rainfall, which is really common in temperate zones. This is basically a violent collision, where a fast-moving, heavy mass of cold air acts like a wedge. It aggressively shoves lighter, warm air upward, causing widespread precipitation all along the boundary between the two. And sometimes this upward movement is just so violent, we get something much more destructive than rain. Inside a towering cumulonimbus storm cloud, powerful upward air currents can actually trap water droplets. They get pushed way up into freezing altitudes where they freeze solid into ice pellets. Then they fall, gather a new layer of liquid water, and get shoved right back up to freeze all over again. Layer by layer, they grow into hailstones until they are finally just too heavy for the wind to support. Then they crash to the earth, capable of doing some truly massive damage to crops and property. So let's take a step back and look at the whole picture. From massive solar radiation hitting the tropics, all the way down to a tiny, heavy hailstone falling in a field, the atmosphere is this perfectly interconnected machine. Heat dictates pressure, pressure commands the winds carry the moisture, and cooling wrings it out as precipitation. It really leaves us with a provocative thought. If our climate is just the 4-year average of this finely tuned engine, how might subtle shifts in global temperatures ultimately rewire this entire delicate chain reaction for the next generation? Thank you so much for joining me on this explainer. I really hope you never look at a simple breeze the exact same way again. Keep observing and keep learning.